week and next week. And our Wednesday meetings, we will not do any practical assignments together. We are all already coming to reporting stage. And I know that it's probably a little too much and too hard for last 2 weeks, but we just need to finish semester. So in addition to the originally assigned figures, I'm asking you to complete a little write-up. And before we go to density function, to time-dependent density functional theory, I will just give a quick overview of what one can put in the paper. Just a second. So we are in the, okay, it works, computational chemistry. We are in the last chapter, and we need a couple of things to finish the density functional theory. We already went over absorption spectra and density matrix and transition density, but we need the principle of time-dependent density functional theory and flow chart. And 2 things that we will do on Wednesdays are academic review or mock review. We will bring papers and provide feedback. We will grade, like everyone in class will grade work of someone else. And on in the weekend 2 days, we will do presentations, which will be the last activity in the class. So here is the link to projects that you have selected. And here is a regional assignment that I hope you are progressing successfully towards completion. So, right, if some jobs are not completed, if you need help, please email me. I would be happy to assist. But the idea is that jobs that you have submitted last Wednesday and that have been completed by now will be sufficient to compose these materials. Well, if most of you are in the graduate school, right? Which means you made research your profession. Oh, I think Lola is reconnecting. You've made research your profession, which means on one hand, you just satisfy your curiosity with you learn something new, but on the other one, you need to prove to people around you to get employment and career growth that you achieve something. And in scientific activities, the main proof of success are research publications. So research publications are not just results, but communications, a way to explain it by human words. So we do need to practice a little bit of this activity, and some of you are already authors of scientific publications. Some of you are just starting. So but we all are reading scientific papers, and you have noticed that they are not just a collection of data. There is a story that connects data together and provides, that sets up questions and provides answers. So I'm going to touch it. So your research is either analysis of combination of 2 objects into one and looking on their interaction, or it is looking how the thermalization affects observables, density of states and spectrum for model before and after real temperature, which can be summarized in form of tables. So there will be something new right now. So we in this class are not the first in the human civilization who are trying to communicate ideas to other people. So this idea of communicating not only results of research, but some analysis, ideas, and an attempt to motivate other people to do some specific activity that you desire is a common problem in the human civilization. And there are different cultures around the world, and in each culture this activity is covered. So here I'm giving an example from like Western European countries, but there are analogs in other cultures as well. So so here are some quotes from, you see this little links on the bottom. So it's Roman and Greek cultures, and in the Greek culture, which one of the best examples is Socrates and Aristotle, they consider this activity of one person talking to a group of people as rhetorics, and he was writing little compositions of how to analyze, how to look on it, so that one needs to actually design what to say, one needs to select a style, one need to arrange the findings and their analysis in most logical way. And on the next slide, I will focus primarily on this little part of how people communicate. So organizing the arguments in a logical way. And other things are not needed because we have like computerized memory and PowerPoints and things like that. So let me check if anyone in audience today was ever taking courses in ancient Latin. Maybe not. I wasn't, but just show yes or no. Did you took any Latin? Okay, thank you, Anand. Hanmant? No. Amir? Oh, okay. No. Lola? Oh, someone is typing. Maybe it's Lola. No. Okay. I'll try my best. But so here I'm going to just try to pronounce, but it is different language. I may pronounce in a different way. So according to Romans and Romans philosophers and Romans public speakers, a goal of any public speech and any human communication and any written document has a threefold. So delectare, dicere, movere, which is translated as to please, to teach, and to move, to urge forward. I'm not a good example myself for this aspect, but it is like ideal arrangement of public presentations and documents. So when you create a document, when you communicate to people, even if you do not realize, there are three goals. First, to please those who are listening to you, because if you're telling something unpleasant, people will just vote by their feet and stop attending, will just leave the room. To teach, because people are curious and happy to learn something new, and to move, to urge forward. Like if you are speaking to people, you are delivering a message to them if you want them to perform a specific activity. Like historic examples, like if military reader wants to motivate his or her little army, or if an attorney wants to convince judge, or if a salesman wants to sell something, just to move, to urge, to induce those who listen to you to do something. And it is just summary of how it works. So if we realize these goals, we can organize our communications in a better way. Let's try to go forward. Okay. So this slide I like at most. So it is a summary of principles for logical organization of your writing or your human communications by Roman philosopher and public speaker and politician Cicero. He did a really good summary of how to be efficient. So it's not the ideas, but organization of the talk. And modern science, in some sense, are following him, although he's not the only one. There are analogs in any culture. So, according to him and according to this Wikipedia article, there are 6 parts of each human communication. So, I will typically, at least one person in the class speaks Latin, and then it is a nice exercise to ask someone to read. Maybe let me assign. Let's rotate. Hanman, would you try to read the first word in blue?
Exordium.
Okay. Yeah. Thank you. So this means like. We can translate it as introduction, but in sense it is like urge forward. So it is analog of abstracts in scientific papers where one summarizes why the reader should read the rest of the document further. Anand, would you like to read the second word in blue?
Narratio.
Okay, so it sounds like the English word for narrative, right? And it is a part of what we put into the introduction part, introduction of our papers. So it tells what is the story about the case. Were there any other people who studied it, what they achieved? So the literature review. Lola, would you like to read the third word in blue?
Partition.
Okay, yeah, thank you, Lola. So it looks like to split things on a part. In modern papers, at the end of the introduction, people sometimes mention how the rest of the paper is structured, like table of contents. Or one can correlate this ancient part with method section. So when one adds logic and explain how the case will be proved. Okay, now let's rotate and do one another round. Hanman, would you read the fourth word in blue?
Confirmatio.
Okay, so it also it sounds like we know Latin. It sounds like confirmation, right? The proof. So it corresponds to the main part of modern scientific papers, results. When one validates, when provides proofs of the statement that the author wants to deliver to the audience, to add credibility, to explain why the figures and tables exactly serve main question that we started earlier. Okay. Anand, would you try to read the fifth word in blue.
Yeah. Paro ratio.
No, the previous one. Here that I'm showing.
Okay, previous one. Confutatio.
Okay, yeah. Thank you, Anand. So it is a very important aspect that some of the modern scientists, especially the beginners, may miss. So, and it is a very deep thought. So while the speaker or author is planning communications with others, he or she should understand that the part of the audience, parts of your readers will disagree with your statements, will tell that your results are wrong or your arguments are not strong enough, or you didn't consider some important aspects. So even if you do everything perfectly, you should assume and expect that some people will disagree with you. And in this section, one prepares to fight against those who disagree. One prepares arguments. So you think ahead what can be suspicious in your work, and you prepare to defend your work. So in modern science, it corresponds to discussion section. And if you get a skill to build this section, then you will have much better success rate in publishing your results and getting grants funded at some stage of career. Someone is typing. Check. Yeah, okay. Yeah, Amir, do not worry. You can watch the recordings later. Lola, would you please read the last word in blue?
Error ratio.
Okay, thank you. So it's like per mouth, like one take a so it's summary or conclusions in modern scientific literature. And what I specifically like in this little summary from the Wikipedia, that the ancient conclusions has a goal not only to summarize what you found, but also create negative emotions against those who disagree with you, and create positive emotions to the author and the case. So it looks a little more like attorney prepares to defend the case, but it is what was taught by ancient speakers like 2,000 years ago. Hello, Amara. Nice seeing you connected. Let me make you a co-host. Okay, so this was ancient ways to organize write-ups, and in modern science we rearrange them in a little more shorter way. So the abstracts can be left out if the work is very short. So basically, first three things can be combined into introduction, and maybe the third one can be methods. Then the fourth part, the proof, is the main part of modern scientific literature, is the results section. Sometimes results and discussion are combined in one section, and then conclusions are still present in whatever scientists are writing. So what do we write in the introduction? I'm going to say something very, very silly. So please, and I apologize ahead because it is oversimplified thing. I'm confident you can do much better. You can do your introductions much smarter than what I'm showing here. So, imagine readers of your term papers may not understand why you are doing a research. Even in this little class, we have quite diverse areas of interest. And in order to attract attention and convince the reader that you're doing something valuable, you need to explain in a very simple way what you're doing and who is getting benefit. So who is getting benefit of your research activity? It sounds oversimplified, but it is sometimes it is very important to convince people to follow you. So here I'm, again, very oversimplified example. So we are doing some sort of, like, suppose we are doing some sort of science and some research, and this research activity here at, let's say, at the university has several outcomes. So it creates papers, publications, patents, and they can be imported into industry, right? Based on your discoveries, some new materials can be synthesized, fabricated, and used in the industry. And then, for example, it can be used in getting energy, or getting new electronic devices, or new medications, or something to increase security. And all these little things positively affect the life of regular citizens. So if you can give an example how your activity help regular people, it's really good start of introduction. It can be made in one sentence. And then citizens pay taxes to federal government, and government sponsors research again. So it's a closed cycle. There is an additional leg. So due to scientific activity, there is a training for new researchers, new workforce who later come to industry and do all this stuff, or through training when prepares new teachers who do general education and also serves scientists. So it is oversimplified, too general, but just giving you an idea how to start an introduction. Okay. So what do we put into the paper, supposing that your figures and tables are ready? So here is an example how to make it really short. So introduction, why system is interesting, if possible give a reference. Identify open problem for your system. So since you selected your object, you already know why it is important. Then here is aspect that I want to focus your attention at. So if there is an open question, as an expert in your field, you already hypothesize, you kind of know the answer, or based on what you found in your research, you can already put it here at the introduction. So when a reader goes and reads it, he or she doesn't know what will be the after, but if you give a hint what would be the answer to the question, the rest will be read much easier. And then you can make a statement that computation by some way can prove this hypothetical answer is correct or wrong. Method 2 section help reader to reproduce your results, and this is a place where you can show several equations, like how DFT is working, or how molecular dynamics helps to find interatomic distances, or how did you compute spectra. So just maybe mention functional and software, but it can be very brief, like a paragraph or maximum half page. And then the main part of your written work is results and discussion. So basically you write a couple of sentences about each figure. So explain what is computed and why the result looks a specific way. So in the conclusions, you should return back by your thinking to the introduction and tell, okay, the results did prove that the hypothetic answer was correct. So basically, the whole paper is set up to prove that there is a question, there is a potential hypothetic answer, there are proofs of this answer, and then you confirm, yes, it was found correct. And if you have any additional arguments to tell that your results are trustable, that you used best possible methods, or you know how to improve them, you just mention it in your paper. And it's good if you have several references, although I know that on short notice, it's not always possible. Okay. I'm just reducing noise here in the room. Yeah, it's just illustrating how the discussion section is going. So prepare to defend your ideas. Okay. So we spent like 40 minutes. In the remaining 20 minutes, I will continue towards the class activities, but I'm sure we will finish it in the remaining lectures. So here is a way how you compute absorption spectra, right? Probability to absorb light as a function of frequency. Just go over oscillator strengths and transition energies. And TDDFT theory must provide us this oscillator strengths, which can be expressed in terms of the transition dipole, selected here in purple. Okay. So, yeah, right here, equations mean much less. I invite you to listen to several words that I'm going to declare. And those words and these methods would be most important to those of us who are looking forward to continue computational research and to focus on reproducing spectra. So if you look to show the absorption or emission spectra of certain materials and molecules, then this next slides and the rest of the academic part of the semester is important. We do not have time to implement all these ideas into calculations, but we need to be aware of it. So the goal is to find the oscillator strengths and transition energies. And the idea behind this theory is that when the molecule is placed into oscillating electric field, which is shown here, like electric field cosine omega t with electric field strength, then the wave function will be oscillating, will get an additional contribution, which is shown here as a psi with uppercase 1, which will oscillate with the same frequency. So the wave function, or later on we will project it to the density, will have a major component that is not changing, plus little oscillating segment. And depending on frequency, this oscillating segment will behave differently. So we need to see a response of a model to external oscillations. This formulation, such formulation of a question is a part of so-called time-dependent perturbation theory. It is an advanced chapter of physical chemistry, physics and quantum theory that sometimes is skipped from courses, but it's quite simple theory. With proper time, one can easily get through it. But here, let me summarize. So what I'm showing is not a complete derivation. It's only ideas. So we do have total density, which is composed of the density without perturbation plus a little change to the density, which can depend either on time or on frequency. Because like amplitude of all changes is just an amplitude, which will be different for each frequency. As we discussed in our previous meetings, this little addition that we get to the density due to external field is so-called transition density, right? The contribution to density that appears if system experiences transitions between different states, which we will call like X and Y. So this transition density will be different. It should be recomputed for each frequency of external electric field. Now, if we perturb our system with external electric field, it means the total energy, and total energy is summarized with letter H, Hamiltonian, will also get perturbation. We'll also get an additional term due to interaction with electric field. And this term of interacting between molecule and electric field, we already discussed it, is transition dipole times electric field times this oscillatory part, right? Please confirm if you, with thumb up, if it makes sense. So dipole times electric field is interaction. Okay, yeah, thank you. So we are trying to make a set of equations that will look how the transition density is affected by interaction energy and in turn depends on frequency of input electric field. It is possible to derive line by line, and it is not a terrible derivation, but it is a little more than we have time right now. And the things that we need to find are these transition densities. Okay, so suppose we have solved this problem. Suppose we already found at which transition energies the molecule is responding to electric field. If it would be a very long, rigorous course between previous slide and this slide, I need to show another like 40 slides of derivations. But let's go right to analysis. So if you haven't fallen asleep yet, if you have some energy, this simple figure is very deserving your attention. I take responsibility that this is a really good figure. So please focus on it. Okay, what does it show? It shows optical excitations, absorption, from in two pictures, so-called orbital picture and excitonic picture. Here in class and in your mini research projects, we were using only orbital picture. It's not very precise, but it's super easy to understand. It's really matching the human style of thinking. But to have the more general vision of this problem, we need to convert, we need to translate orbital picture into excitonic picture. So although we do not have too much time, I'm slowing down here. So if we are looking on the absorption in the orbital picture, we have occupied, highest occupied -1, and we can promote an electron from HOMO to LUMO, or from HOMO -1 to LUMO +1. So if we consider only 2 occupied and 2 unoccupied, I just missing one line, there will be total 4 transitions, right? So if you do, hello, payment, happy to see you connected. So if you have 2 occupied and 2 unoccupied, there are 4 possible transitions from each of 2 occupied to each of 2 unoccupied. And they will have different frequencies. The transition from HOMO to LUMO will have the smallest energy, right? And the transition from HOMO -1 to LUMO +1 will have the biggest. So 4 transitions. Now, let's think. So what I'm going to say is simple, but we need to concentrate. I will slow down and reiterate. We do have 4 transition energies at which light can induce transitions. If we haven't started exciting our system, it is in the ground state, right? Ground state when all electrons are staying in the occupied orbitals. In the excitonic picture, we can tell it's like ground state number 0. Then if we remove electron from HOMO and place it to LUMO, it will correspond to the lowest excited state. So excited state number 1, E sub 1. So under E sub 1, we should understand from HOMO to LUMO. Then if you have from HOMO to LUMO +1, it will be a little bit higher energy, E2. If you excite from HOMO -1 to LUMO, it will be a little higher, E3. If you excite from HOMO -1 to LUMO +1, it will be bigger, E4. But in the orbital picture, we always speak about pairs of orbitals. In the excitonic picture, we speak only about one number, transition energy. And when people analyze results of TDDFT, they do not use pairs of orbitals. They speak only about transition energies and oscillator strengths corresponding to transition. So the picture, excitonic picture, is more correct. And just if you will be presenting your results on scientific conferences, writing papers, communicating with colleagues, just keep it in mind. If you explain everything with orbitals, it can be too simple. So the best way is to tell, like, we recognize this excitonic picture, but we want to do quick, simple calculations. Therefore, we return back to orbital picture. Make sense? Please confirm if with thumbs up if this makes sense. Thank you, Hanman. Thank you, Anand. Thank you, Lola. Thank you, Amara. Let me just pull a little. Payment, does it make sense? You can speak, type, or just show thumb up or thumb down. Yeah, okay, yeah, thank you, Payment. Okay. Yeah, so same idea, just with more details. And here, let me introduce an equation. Again, I'm not showing derivations. Maybe in tomorrow and next week, I will tell a little bit more, but here is an equation that we need to focus on and study. So this equation provides an answer to the TD-DFT formulation. So it is an equation which software is solving when we request TD-DFT calculation. So instead of deriving, I'm just introducing it. So what this equation is and what does it give? So this equation does have this unknown x sub I and y sub I on left and right. And it has unknown omega sub I. And it looks like a matrix, vector, number, and vector. So by mathematical structure, it is an eigenvalue problem. So this eigenvalue problem is very similar to Schrödinger equation, which we were solving before for the whole semester. But when we speak about Schrödinger equation, it gives wave function, right? Orbital. Here, it gives us transition densities for excitation and de-excitation, and transition frequencies or transition energies if we multiply it by Planck constant. So the main equation of time-dependent density functional theory is an eigenvalue problem that gives us set of transition frequencies and corresponding transition densities. It is not the last time to describe it. We will refocus on it tomorrow and next Monday. So the name, the gentleman who designed this equation, his name is Cassidy, so it's Cassidy equation. And it gives multiple answers, like several transition frequencies, several transition densities. So those of you who already practiced TDDFT calculations in Gaussian software may confirm that TDDFT calculation provides several transition energies. Lola, would you confirm?
Yes, it does.
Oh, okay. Yeah, thank you. Thank you, Lola. Okay. So now the next question is, what are these A and B objects in this equation? And how generally they are related to the things we did before in the class. So in case, let me restart. I need to cut 15 seconds and restart. Main benefit of the time-dependent density functional theory is that it takes into account attraction of electrons and holes. It shows transition energies different, slightly different than difference of orbital energy. But if we disable, if we forbid electrons and holes to attract each other, then we will have only A coefficient and only the thing that is highlighted with green. So if we forbid electrons and holes to attract each other, then the term A will be a matrix that will include only subtraction of occupied and unoccupied energies. And as a result of Cassidy equation, we will get absolutely the same transition energies which are equal to energy difference between occupied and unoccupied orbitals. This is not always correct. Sometimes electrons and hole with positive negative charge attract each other. Like hole means absence of electron in the orbital where we took it from. Now, what are the other terms which are non-zero? Those are different forms of Coulomb interaction between orbitals. Here are the notations. Latin indices at the beginning of alphabet. A stand for unoccupied orbitals, or instead of electrons, in the community of this theory, people call them particles. Like electrons are particles. So E sub A, and here are particles. The second part of alphabet, starting with I, stands for holes. And here we are looking for one electron hole pair, IA, and another electron hole pair, JB, interacting to each other. And there are several four particle interactions. So this round bracket notations is open here. Like if you have IA, JB, it is this anti-symmetrized Coulomb. And in a way how it is formulated here in the first 1, 2, 3, 4 lines, it is the older version of the theory, time-dependent Hartree-Fock, when we literally look for interaction of orbitals. In the TDDFT, this explicit Coulomb interaction is replaced by second derivative of total energy, or exchange correlation part of total energy, in respect to the density. So before, when we used regular DFT, we had a first functional derivative of total energy in respect to density. Now we have a second derivative. Okay. Please confirm if this idea looks okay. If just generally, if you didn't found any major confuse, or show some. Okay, yeah. Thank you. And let's look if you have anything else. Yeah. So this transition density is basically deal with different segments of density matrix. Right now, I believe it is time to finish. But when we will go further, the next thing I will start tomorrow will be this slide with a little derivation where we will slowly discuss how the knowledge about transition density allows to find transition dipole and oscillator strengths. So basically it is already shown here. So if you know the density, we can find the dipole, and from the dipole we can find dipole squared, which will be oscillator strengths. So it's a brief summary. But I believe right now we are coming close to the time limits, and I suggest we just stop here. So meeting is done. Everyone is welcome to disconnect. If there are quick questions, please formulate them. If no, looking forward to see you on Tuesday lecture at 11 and on Wednesday meeting, when everyone is invited to bring 3 printed copies of the draft of the term paper. So do not worry, do not panic. You need to work and prepare these drafts, but it will be the first draft. There will be chance to improve it. And the final draft will be due early morning on next Monday. Okay, so meeting is done.